Okay, so have you ever just felt like the universe is messing with us? Like what we see isn't really all there is? Well, get ready because today we're going deep into wave mechanics with our expert, and trust me, things are about to get seriously weird.
Hey, no, it's funny you should say that because even before Schrödinger physicists were already kind of wrestling with this whole idea that things aren't always what they seem.
Really?
Like light, right. Sometimes it acts like a wave, creating these really cool patterns like when you look through a telescope.
Oh, yeah, diffraction patterns.
Exactly. Diffract, but
Yeah.
then you have these tiny little electrons, the things that make up literally everything.
Hmm.
And they seem to be playing by a whole different set of rules.
Right, because you'd think if they're the building blocks of matter, they'd have to follow some kind of predictable path, right?
Well, that's where Schrödinger comes in, like a rock star with his big idea.
Yeah.
What if he said electrons weren't just these little particles, but also had wave-like properties?
Whoa. Okay, so not just tiny balls of stuff, but also like ripples in a pond.
Kind of. But instead of a pond, imagine a three-dimensional cloud of possibilities. It's called wave-particle duality. This wild idea that something can be both a wave spread out everywhere and a particle at a specific point at the same time.
My brain's already hurting in a good way, I think. But
Oh,
wait, you mentioned telescopes earlier. How do they fit into all of this?
think of it like this. Even the best telescope has limits, right? There's always going to be that little bit of blur around the edges of things because it can only take in so much light. Well, classical physics hit the same wall trying to understand the really, really small stuff, like electrons.
So classical physics was like that toy telescope you had as a kid. Fine for looking at the moon, but useless for anything more complicated.
Exactly. Schrödinger was saying we need a new lens, a whole new way of looking at things to wrap our heads around something as slippery as an electron.
And that's where this diffraction halo thing comes in. It sounds like something straight out of Star Trek.
It does, right. But it's actually crucial here. Imagine dust motes in a sunbeam. You know how they seem to glow? It's not because they're making their own light. It's the light scattering around them, creating that fuzzy glow.
Okay, so the dust is like our electron, and the scattering light is like its wave-like behavior.
You got it. It's like the electron isn't just one point,
Yeah.
but this wave spread out interacting with its surroundings.
So instead of a clear path, it's more like a cloud of maybes. The electron could be anywhere in that cloud. But how does this connect back to the whole atom?
And this is where Schrödinger's genius really shines. He suggested that the atom itself could be thought of as the electron's diffraction halo.
Wait, so the whole atom, everything is just this big blurry electron wave. That's a lot to take in.
It is. But that idea right there, that's what changed everything about how we understand atoms. You see classical physics with its neat little orbits around the nucleus, well, just wasn't telling the whole story. Schrödinger showed us that to truly get atoms, we had to embrace the weirdness, the wave-like behavior of electrons.
So instead of those nice clean orbits, we're talking about this fuzzy cloud where the electron could be anywhere.
Yeah, it's like you're trying to find one specific ripple on a pond. It's not in just one spot. It's spread out.
Hmm.
And the size of that cloud, the atom itself, it's directly connected to the wavelength of its electron. That's what's so amazing about Schrödinger's equation. It ties the big stuff we see to the tiny quantum world.
It's like one of those magic eye pictures. You have to unfocus your eyes to see the hidden image. Like there's this whole other layer of reality right in front of us, and Schrödinger gave us the key to unlock it.
And the coolest part is that his work wasn't just theoretical. His equation, as crazy as it is, had real-world uses. Scientists could actually use it to predict how atoms would act and then test it out. It was a massive leap forward in how we understand the universe at its smallest level.
It's like he invented a whole new language to describe the universe. You know, as much as he cleared things up, he also seemed to like pushing the boundaries of what we thought we knew about reality.
Oh, totally. He challenged that old idea in physics that everything is predictable if you just know the starting conditions. The wave mechanics brought uncertainty into the spotlight.
And that's where the whole either or versus both and thing comes in, right?
Exactly. Classical physics was all about either or. An electron was either here or they're moving on this path or out of that one. But Schrödinger's wave mechanics said, hold on, it's way more nuanced than that. It's not that the electron is randomly jumping around. It's more like we can't know both where it is A and D, how fast it's going at the exact same time. It's like just by looking at it, we're affecting it.
So it's like the electron is saying, hey, scientists, make up your minds. You want a wave or a particle this time?
I like that. That whole observer effect really shook things up. It made everyone question what's really real and what we can actually know.
It's giving me an existential crisis about free will. If something as basic as an electron doesn't follow a set path, what does that say about the choices we make? Are we all just blurry waves too?
You're getting at the heart of Schrödinger's impact. It wasn't just equations and particles. It was about changing how we see what's real and what we can know. He made us confront the limits of our everyday understanding and embrace the strangeness of quantum mechanics.
It's kind of awe-inspiring and terrifying all at once. So where does that leave us? If everything around us is made of these wave-like particles that break all the rules, what does that mean for the universe itself? So are we saying the universe is like less like a clock and more like a wild ocean?
It's actually a really cool way to think about it. And, just like an ocean has currents, the quantum world has its own kind of order patterns underneath it all. Schrödinger's equation helps us make sense of those patterns, even though we're still figuring out what it all means.
It's like he gave us this map, but we're still exploring, discovering new things all the time.
Exactly. And the crazy thing is how Schrödinger's work has gone way beyond just physics. It's had a huge impact on chemistry, biology, even computer science. It just goes to show you how these fundamental discoveries can change how we understand everything.
You know, thinking back to that blurry electron picture, it's almost poetic in a way. It's not that it's meaningless, it's that it's something way bigger and more complex than we ever thought.
I totally agree. And maybe, just maybe, that feeling of infinite possibility goes beyond just the tiny stuff. If everything around us, even us, is made of these wave-like things, always changing, always interacting well, it makes you think, doesn't it?
It really does. It's like Schrödinger left us with this universe full of unanswered questions, this
Yeah.
giant mystery that's still unfolding. So to everyone listening, the next time you look at something, anything really, take a second to think about those blurry wave-like things that make it up. Who knows what else they can tell us about what's really real. That's all the time we have for our deep dive today, but the journey into the quantum realm, well, that's just getting started.